Okay, so in this video, we're going to talk about another bad property of the rational numbers, which is another aspect of its incompleteness, and it's called the analytic incompleteness. So what does it mean? Well, it means there are some sequences. There are sequences in the set of rational numbers Q that approach to a number not in Q. Okay, so there are some sequences which consist only of rational numbers, and they approach to a point, they approach to a number, but that number is not a rational number. Okay, so for example, let's consider the following sequence: 1, 1.4, 1.41, 1.414, etc. So these numbers are all rational numbers, and they approach to the square root of 2. They approach to the square root of 2, and according to what we just proved in the last video, the square root of 2 is not a rational number. Okay, so now we need to prove the analytic incompleteness. Okay, so let's consider two sets. Consider A. A is the set of all the rational numbers P, where P is positive and P squared is less than 2. And another set B. B is a set of all the rational numbers P, where P is positive and P squared is larger than 2. Okay, so our claim is the set of A has no largest number. Okay, so that's the first part of our claim. And the second part is B. The set of B has no smallest number. And as you can see, the sequence we have just mentioned above, this sequence, these numbers are all in the set of A, and it's getting larger and larger, and it's getting closer and closer to the square root of 2, but it never actually gets there. Okay, there are no largest number in this set. So how do we prove it? So let's first prove the first part of the claim. Well, A, the set of A has no largest number. What does it mean? Well, it means that for any number in A, there is a larger one, right? So let's write it out. Okay, so for we need to show, okay, for any number, for any P in A, there exists a Q in A such that Q is larger than P. Okay, so this symbol is a notation, the backward A is a notation for any. Okay, so for any P in A, there exists a Q which is also in A, and the Q is larger than P. Okay, so now the point is, how do we, given a P, how do we choose that Q? Okay, so let's use some trick here. Okay, so let's draw a graph of the xy plane. This is the xy plane, and this is a graph of the function y equals x squared minus 2. Okay, So the x-intercept of this equation is the square root of 2, and the point P lies somewhere between 0 and the square root of 2. And let's just call this point A. Okay, so the coordinates of A are P and P squared minus 2. Okay, so now we need to choose a point between P and the square root of 2. Okay, so how do we do that? Well, so we pick a point on the right hand side of the square root of 2. Okay, let's say we pick 2. Okay, and let's call this point B, and the coordinates are 2 and 2, right? So, and then we connect A and B, and the coordinates we get, the x-intercept of A and B is exactly the Q we're looking for. Okay, so how do we get that Q? Well, since we know the coordinates of A and B, and we know the equation for A and B, for AB, for the line AB, right? And we set y equals to 0, and we get x-intercept, and which is Q. Okay, so the formula for AB is y minus 2 equals p squared minus 2 over p minus 2 times x minus 2. Okay, and this is the slope of AB. Okay, so we set y equals to 0, and that equation becomes negative 2 equals p squared minus 4 over p minus 2 times x minus 2. Okay, and so let's solve for x. So x, well, through some calculations, and we find x is 2p plus 2 over p plus 2. And that's exactly the Q we're looking for. And since p is a rational number, then 2p plus 2 over p plus 2 is also a rational number. So Q is a rational number. And now we need to verify that the Q we get from this graph actually satisfies our conditions. Okay, so we need to verify two parts. The first part is Q is larger than P. So to do that, well, let's calculate Q minus P, which is 2p plus 2 over p plus 2 minus p. And that is 2p plus 2 minus p squared minus 2p over p plus 2, and which is 2 minus p squared over p plus 2. And since p squared is less than 2, 2 minus p squared is positive. A positive over positive is positive. Okay, so this thing is positive. And so Q is larger than P. Okay, so that's the first part. And the second part we need to verify is Q squared is less than 2. Okay, so again, we calculate Q squared minus 2, which is 2p plus 2 over p plus 2 squared minus 2. And that is 4p squared plus 8p plus 4 minus 2p plus 2 squared over p plus 2 squared. And that is 4p squared plus 8p plus 4 minus 2p squared minus 8p minus 8 over p plus 2 squared. And we cancel out to 8p, and we get 2p squared minus 2 over p plus 2 squared. So p squared is less than 2, then p squared minus 2 is negative, and negative over positive is negative. So this guy is negative. And so q squared is less than 2. Okay? So given a number p in the set of A, we find a q, which is also in the set of A, and it's larger than the number p, right? So for each number p, there's always a larger number. Okay, so that means the set of A has no largest number. Okay, so the second part is pretty much similar. So the second part claims that B, the set of B, has no smallest number. And what does it mean? Well, it means that for each number in the set of B, there's always a smaller number, which is also in the set of B. Okay, so we need to prove for any number, for any P in B, there exists a Q in B such that Q is less than P. Okay, and surprisingly, the Q we got from the first part of the claim actually works for the second part also. Okay, so for the first part, we find that Q is 2p plus 2 over p plus 2. Okay, and this actually works for the second part. Okay, so I'll leave you as an exercise. So the exercise is verify q equals 2p plus 2 over p plus 2 works. Okay, so to verify that q works, basically you need to verify two parts. The two parts is, the first part is you need to verify that q is less than p, and q squared is larger than 2. Okay, so that's for this video, and thank you all for watching.